G'day viewers. In this episode we're going to take the particle-antiparticle pair representation developed by Tshipa to a new level and imbue it with capabilities that Tshipa did not envisage. We're going to align Tshipa's model with the electrogravity-magnetic construct, thereby deriving important quark information. En route, we shall establish three significant quark characteristics. Number one, the typical quark form factor is a solid ellipsoid, specifically a spheroid. Number two, the typical quark radius is approximately 0.53 attometers. That is, the typical quark diameter is about 1 attometer. Number three, the neutron and proton are approximately 1,558 times larger than the quark, on average. Okay, let's get into it. Let's begin our journey by identifying where the Tshipa research article can be found, as we did in episode 98 and 99. Now that you know where to find the primary artifacts, let's expand Tshipa's particle radio model to include quarks. If you have not already watched episode 98 and 99, please pause this presentation and watch the previous episodes before proceeding. Well, assuming that you have followed my instructions, let's move on. Before we embark upon a quark radii solution, we shall leverage off the results we obtained in episode 99, whereby we utilised established experimental benchmarks to act as frames of reference. We recommend all viewers to watch episode 5 on this channel for a video presentation pertaining to the formal derivation of the zero-point field equilibrium radii appearing on screen. It should be noted that the zero-point field equilibrium radii we derive coincide with the proton root mean square charge radius and the neutron mean square charge radius. This means that the zero-point field equilibrium radii equations appearing on screen may be considered to be authoritative and definitive. At the bottom of the screen, we compare our spin angular momentum solution to the benchmark zero-point field equilibrium radii solutions appearing mid-screen. Our results show that the dissimilarity between the tabulated information and the experimentally verified benchmarks are minimized as indicated by the purple emphasis. In the case of the proton, the best fit occurs when I sub x equals a half, such that the deviation from the experimentally verified benchmark is less than 0.08%. In the case of the neutron, the best fit occurs when I sub x equals 2/3, such that the deviation from the experimentally verified benchmark is less than 0.008%. Now that we have reviewed the results obtained in episode 99, we can embark upon our quark radii solution. It may seem astonishing to many viewers, but there are only two particles which have had their physical dimensions measured to high precision, that is, the proton and neutron. Even then, of these two particles, neutron size measurements are not as straightforward or precise as the proton. In fact, the size of the neutron is actually measured as a negative squared quantity, then converted to a positive valued quantity as appears on screen. This means that an experimentally direct like-for-like size comparison between the proton and neutron isn't actually possible. It can only be inferred. Once again, we recommend all viewers to watch episode 5 on this channel for a video presentation pertaining to the formal derivation of the size of the proton and neutron. Okay, so what does all this mean and where does it leave us with respect to a quark radii solution? Well, given that the proton and neutron contain up and down quarks, we need to find some common ground. By inspection of the neutron dissimilarity results, we can see that the I sub x equals a half solution produces a dissimilarity result of less than 0.4%. Thus, we shall assume that the proton solution is common to all baryons. Consequently, we shall model the neutron as a rotating disk, as we did with the proton. Okay, let's now visualize what we mean. The most precisely and accurately measured particle size dimension ever gathered is associated with the proton. Hence, we shall assume that the shape of the proton is common to all baryons. We shall interpret the two dimensions generated by the spin angular momentum inclusive form of particle radii as disk radius and disk thickness. We have determined that a rotating disk fits the experimentally verified root mean squared charge radius of the proton to within less than 0.08% error, or in other words, to greater than 99.92% similarity, that is, accuracy. The obvious question now arises, how can we visualize the up and down quarks associated with baryons, specifically the proton? Well, as indicated by the illustration, the quarks reside within a so-called probability domain. This probability domain denotes a three-dimensional volume containing dynamic location information. Of course, it follows that the form factor of the quarks, that is, their shape, aligns with the environment in which they reside. Let's now derive a particle-antiparticle pair representation estimate for up and down quark radii. To facilitate this, we shall assume that the absolute value of R sub beta s represents proton root mean squared charge radius. Hence, it follows that the quark mean squared charge radii may be directly proportional to the dimension of the minor disk axis and the ratio of quark mass to baryon mass, according to the relationship shown. Executing the process as indicated on screen, we can see that the average particle-antiparticle pair representation estimate for up and down quark radii is approximately 99.5% similar to the equivalent electrogravimetric estimate. This is a very encouraging result because it demonstrates that the particle-antiparticle pair representation model aligns well with the electrogravimetric construct. Okay, we have derived particle-antiparticle pair representation estimates for up and down quark radii. Let's now derive a radii solution for the remaining quarks. In order to derive quark radii estimates for the strange, charmed, bottom and top quarks, we shall leverage off the methodology presented in episode 8, that is, in our periodic table of harmonic solutions. Please review episode 8 if you have not already done so. You will see that we have been able to formulate a harmonic representation of fundamental particles. It is worth your while reviewing, so please try to find some time to have a look. Our derivation commences with three basic assumptions / simplifications. Number 1. All quarks are related to baryonic matter, represented by the mass of the proton in calculations. Number 2. The radii of all quarks reside within the approximate vicinity of the average up and down quark radii stated on the previous slide. Number 3. All quark radii are harmonically quantized relative to average up and down quark radii, represented by K sub Q. The solution algorithm appearing on screen should be straightforward, easy to follow and self-explanatory. In the bottom right-hand corner of the slide, you can see that the similarity between the average electrogravimetric quark radii and the average particle-antiparticle pair representation of quark radii is approximately 85%. This is a favourable and noteworthy result. Utilising this similarity result, we can predict an improved form factor with respect to the shape of quarks. As we just saw a moment ago, we have been able to reproduce almost 85% similarity in quark radii estimates between the electrogravimetric construct and the particle-antiparticle pair representation, based upon the strange, charmed bottom and top quarks. However, if we extend this domain to include the up and down quarks, we can increase similarity to approximately 90%. The assumption appearing in the blue box within the MathCAD computational algorithm is not required in order to calculate the mass moment of inertia configuration coefficient I sub z. The stated assumption is required for the computation of A and B, not I sub z. The fact that the mass moment of inertia configuration coefficient calculated resides between 0 and 2/5 means that the geometric solution we are seeking resides somewhere between a point particle and a solid sphere. Hence, the obvious compromise is a solid ellipsoid. Thus, we can build a MathCAD computational algorithm to deliver a solution for the form factor of quarks in 3 simple steps. Step 1. Select a geometric shape in order to initiate the computational process. In our case, we selected a solid ellipsoid as our starting point, as justified a moment ago. Step 2. Set the condition that the average electrogravimetric quark radii is equal to the average particle-antiparticle pair representation quark radii. Please note that the averaging coefficients vanish from the equation, yielding the appearance of sums. Step 3. With the MathCAD computational algorithm having determined that the geometric solution is spheroidal, we assigned an appropriate set of axes scaling factors. In our example, we have scaled C to be 3/5 of A. Let's now summarise what we have learned. On our journey, we have aligned the particle-antiparticle pair representation developed by Tshipa with the electrogravimetric construct developed by Storti and Desiato, consequently deriving important quark information. En route, we have learned 5 significant lessons. Number 1. The typical quark form factor is a solid ellipsoid, specifically a spheroid. Number 2. The typical quark major axis is approximately 0.53 attometers. Number 3. The typical quark minor axis is approximately 0.32 attometers. Number 4. The neutron mean squared charge radius is approximately 1,555 times greater than the typical quark major axis. Number 5. The proton root mean squared charge radius is approximately 1,562 times greater than the typical quark major axis.